Thank you very much, Peter, and thank you also to Marco for organizing this day. So I'm going to talk about things related to haptics, which is the sense of touch, and how to give haptic feedback to human operators who are teleoperating robots or trying to use an augmented reality system such as that might be used for surgical simulation or training. Now, I know there are a lot of people in the audience who are computer vision researchers, and you might be wondering what's so interesting about touch. And I like this way of looking at a comparison between sight and touch, and it may inspire some of you to think about the dual nature of these two sensing modalities, how they have advantages and disadvantages, and how they might actually work together. So just some comparisons. So sight is, of course, relatively centralized, right? Our eyes are in basically one place in our body. Touch, on the other hand, is distributed. We have tactile sensors all over our bodies. At the same time, sight, despite the fact that the sensors are centralized, what we see is broad. I can see all of you just standing over here, but touch yet is narrow. So if I wanted to go over and poke Peter up here, I would have to walk over there and actually physically interact with him, and it actually requires a lot more effort for me than it does to just look at him. Sight can also be passive in a similar way, whereas touch is very active, and that creates a huge challenge, especially for giving touch feedback in virtual or teleoperated environments, because you have to let the user be active. You can't just let them sit. You have to go out and actively acquire the data that you need. And then in terms of, at least for humans, how these senses are processed, a lot of people, neuroscientists, think of sight as a very cognitive process and touch being more physical. For example, we have many reflexes, ways in which we interact using the sense of touch that don't even actually travel all the way up to our brain. We have low-level circuits in our bodies that respond to touch sensations. So they're very different, and they have advantages and disadvantages for different types of applications and uses. So quickly, to give a definition of haptics, so the field of the sense of touch, it really means anything having to do with the sense of touch. It's not a made-up word. You can think of as optics is to vision, as haptics is to touch. And often researchers, both people who study human touch as well as people that develop robotic touch, tend to divide the field into two separate categories. The one on the left being cutaneous or tactile interaction, and this is things having to do with the skin. So we have mechanoreceptors in our skin that can sense temperature, texture, slip, vibration, and even local pressure or force. Whereas the kinesthetic sensing on the left has more to do with large-scale configuration or motion. So for example, proprioception is our ability to know where our limbs are in space. So if you put in a hat or you try to touch your fingers together over your head, these are things that we do because we sense large-scale motions and forces in our limbs. And you can also use this to measure environment forces like compliance and such properties. So these haptic senses, both the cutaneous side and the kinesthetic side, all work together with the motor control system to coordinate movement and enable perception. So in my laboratory, we're very interested in medical robotics, and Ken Goldberg actually talked quite a bit about robot-assisted surgery, or in his case, robot autonomous surgery. But what is actually used clinically today are robots like this one. This is the Da Vinci surgical system, which is teleoperated. So a human operator sits at a master console, manipulates some master devices, and much like Stephen Boyd said, through something that's pretty much your typical PID type controller, a slave robot tries to follow those movements of the master manipulator. And the challenge here for haptics is how do you give feedback to the human operator so that the human feels like they're operating directly on the tissue and using the instruments such as and materials like sutures, rather than the whole interaction being mediated by a master robot, a controller, and a slave robot. Can you get a sense of transparency so the human operator feels as if their hands are directly inside the patient and getting all of that useful tactile sensing capability and force sensing capability, which currently is not available in clinical systems for some reasons that will become apparent as I keep talking. So I first want to talk about force feedback, even though my talk mentioned tactile feedback, because force feedback actually has a much richer and longer history in the field of haptics. So the idea here is that if you have a remote robot that's pushing on an environment, you can actually feel the forces. And you can also use sensory substitution of that information, like that bar graph, which is an artificially overlaid visual display of how much force is being applied at any time. The picture on your right shows an artificial calcified artery. In our case, it's a coffee stir straw, which is embedded in artificial tissue, which is supposed to feel, according to the surgeons, like a calcified artery when you're doing heart surgery. So if you want to look at the value of having force feedback in a situation like this where you really can't see that hard occlusion, you have to feel it because it's inside opaque tissue, you can do human user studies, which is a lot of what we do in our laboratory, to evaluate the effects of haptic feedback. And so this shows one example of such a study where we have cases where we have both haptic and this graphical sensory substitution together, giving feedback to the human operator. The green case is haptics only, so they still get the normal visual feedback, but there's no augmented reality, so that's just force feedback. And then there's the graphical only, and the last case is no force feedback provided, just the regular visual feedback. And so low error in determining the angle of our fake calcified artery, low error is good. And so you can see the two cases where you have haptics are much better than the cases where you don't have actual haptics. And in an exploratory procedure like this, it turns out that sensory substitution is not so great. All right. So you could also say, well, maybe we're not just interested in the real-time force that's being applied to the user. Maybe we're interested in the distributed tactile information, and that distributed information could also be sensed palpation by palpation movement and then displayed as a graphical overlay to the surgeon. But we still have this problem that compared to the typical force feedback or this graphical overlay, you could actually do way better with the bare finger. And that motivates having tactile, distributed tactile information displayed to the skin. And there's really two main approaches to do this. One is to use a haptic illusion to trick the user into feeling something they're not actually feeling, and the other is to literally physically recreate the environment's geometry and mechanical properties so that the user can explore it and get that tactile feedback. So I'll give you a couple examples of each. So this first one is a fairly complicated system where you have a tactile sensor on a teleoperated robot that gets distributed tactile information. And in this case, our feedback, if you can see the little video up there, is actually an air jet which is blowing on the skin. And depending on how much pressure and what the size is of that air jet, it actually creates a lump indentation in the fingertip. And that's a very literal recreation of a tactile sensation, which works. Unfortunately, it's also very loud, so it's not a very practical way of doing it. One method we're very excited in our lab about giving tactile feedback as a way to augment force feedback is through skin stretch. And the idea is that if you have a stylus and you're pushing on an environment with that stylus, not only do you feel force feedback, but you feel local skin stretch on your fingertip that tells you how hard you're pushing. So it turns out that we can use a little tactor, like the red dot that's shown in the pictures here, that stretches the skin locally, and this haptic illusion tricks the user into thinking that they're applying more force or feeling more force than they're actually feeling. So it adds on the regular force feedback to this skin stretch, and it enhances the overall sensation of the environment. And so we can use this in a teleoperator. This is an example of someone teleoperating with this type of feedback. And we can get results showing that this sort of skin stretch feedback can do as well as force feedback, that is in terms of decreasing errors, and is much better than other forms of sensory substitution methods. And we've been designing things like 6-degree of freedom skin stretch devices that can go onto the master of a teleoperated surgical robot and be used to give users a sense of force feedback while not having to actually apply force feedback, which can cause instability in closed-loop teleoperation systems. All right. And since I'm being signaled I'm out of time, I'm going to skip over the stuff that my student Andrew already talked about in his poster presentation, and thank all my students for the various devices, control systems, and analyses that they've done in these projects. Thank you.